Hello and welcome back to the Inside Java podcast, the podcast about everything Java, brought to you by the team at Oracle that builds Java. My name is Nicolai Parlog, and this episode of Ask the Architects is a conversation with Ron Pressler, Java architect at Oracle, that we recorded behind the scenes at JavaOne 2026. Ron explains why Java's use of memory, often chided for being excessive, is actually a strength, as it trades more memory use for fewer CPU cycles. Java can only make this trade-off due to its moving garbage collectors, something ostensibly more memory-efficient platforms often cannot. But what's the point in leaving available memory on the table if using it makes your program run faster? Oh, and on the topic of faster, Ron also has a few choice words to share about the use of benchmarking and what to do instead. Enjoy the episode. So, Ron, a couple weeks ago, I asked you to help us out reaching the audience to come here to JavaOne and to record a little short. And you basically, you're like based on your talk here, and you basically told us, yeah, Java uses a lot of memory. But that's not actually a bug. It's a feature, which really sounds just like copium. But how is that possibly true?
Okay. First of all, recording that talk took that short was a lot of effort for me because I'm not used to recording video.
Yeah.
It was the first time I used a real camera. And
video is very unforgiving. Yeah. Like if you do something live and you make a mistake, you just keep going. But if you do a video, for some unknown reason, at least for me, a mental process starts like, oh no, you didn't do it right. Do you want to do it again? And like that one is not only draining, it also leads to way more mistakes in the next couple seconds, and you do start over, and video's hard. So, but imagine this were live. There's no backsies. Anyway,
to your question, the reason it's not to cope is because, well, first of all, my talk is not about how a specific GC in the JDK works, but about the principles behind all of them. And the obvious reason it's not a cope is because that general algorithm, which is called moving garbage collectors, was invented to reduce the overhead of less efficient memory management techniques that we see in many other languages, including anything that's based on malloc and free. And I think that the person who first identified the efficiency of moving collectors is Andrew Appel at Princeton in the 80s in a paper called Garbage Collection Can Be Faster Than Stack Allocation. There is a fundamental problem with memory management, and it takes, because we don't have infinite memory and we have to reuse memory for new objects to replace old ones. That takes some work for the computer. And it doesn't matter if you do it manually, as in C, or with a reference counter garbage collector, as in CPython, or with a moving garbage collector, as in the JDK. And the moving algorithm was created to reduce the overhead of memory management. And that is why Java uses it. We had other approaches in the past. We had the CMS collector, which is very similar to the collector that's used by Go now. We removed it from the JDK, I think, 6 years ago, just because the other approach was better. Yeah.
So CMS is kind of like it works in the same space as G1, right? It tries to be like not have like parallel GCs is throughput oriented.
Yes.
Long pause times if they have to be there, that's fine. And CMS was more like let's concurrent mark sweep, let's do it in concurrency with the application.
Right, but CMS as in Go CMS is not a moving collector.
Okay.
And the idea of moving collectors is that you can use more RAM to reduce the CPU overhead of memory management. So it is an intentional trade-off of using the RAM chips as a program accelerator. Now, the funny thing, and I mentioned it in the talk, is that if you have a program that uses a GPU as an accelerator, people say, oh, that's a very clever program. But if you, as Java does, if you use the RAM chip to accelerate your program, people call it bloated.
Yeah.
But that is what we're doing. We're using more RAM to accelerate the program. And that is why Java handles much higher allocation rates than pretty much any other language. And that's an intentional trade-off. But then the question is, do you want this trade-off or not? Is it worth it for you to use more RAM to reduce your CPU consumption? And the answer is that almost always is also always yes, because RAM is cheaper than CPU. And doesn't matter, even RAM prices are high now.
I was going to say.
RAM prices are high now, but still using even 10x more RAM to save 5% of CPU is still cheaper. And you can look
Financially, is that so?
Yes.
That sounds.
And even if you look at and in the talk I go into numbers.
Okay, so the talk is gonna go live on the Java YouTube channel, or maybe it already is live on the Java YouTube channel. If so, check the show notes. Otherwise, do subscribe. We're gonna release all of this over the next couple of weeks and months, or the past weeks and months, depending on when this gets out. Because I'm gonna warn you right now, this being like more of a timeless topic, you might get bumped to the end of the queue.
Okay. So it is almost always worth it to spend more RAM to preserve CPU, although moving collectors in Java give you a knob. You can say whether you want to use more RAM and less CPU on memory management or vice versa. And there's a knob you can turn, and that's a beautiful feature of moving collectors that other approaches simply don't have. But even at the minimal memory consumption that you have, you say, I just want to minimize memory, it will still be more memory than other approaches.
Yeah.
So that is sort of the trade-off. But we get more speed in exchange for more RAM.
Yeah, I think on the bloat end of things, one reason surely is that Java used to be a desktop technology, and a desktop RAM is potentially a very limited resource, right? People running stuff on their home computer at home. And then running out of RAM and bleeding, which can lead to applications stalling or misbehaving, is generally speaking a more like a more intense nuisance than just a program taking longer. So I think the fact that people are in the past at least had to pay for their RAM to put in their machine and then watch the task manager showing like this much RAM is used by some Notes app that happened to be implemented in Java, I think maybe contributed to that, which is not the world that Java is mostly operating in now, which is as a backend technology where it's not down to how you're feeling about the performance of your system, but like to hard numbers of how performant something is. But even then, isn't Java having a hard time on the smallest of these cloud instances, which often come with like very, very few gigs of RAM?
No. So in the talk, and by the way, the talk was inspired by one given by my colleague Eric Hosteland, and he's an actual memory management expert. He's on our GC team. I'm not, but the way he explained the principles.
Why am I talking to you then, Ron?
Because he's not here. Yes,
Okay.
in fact, I suggested you speak to him.
That's true. That's true because I asked you.
So he gave the talk as a keynote at the International Symposium of Memory Management, but it was targeted an audience of memory management experts. So I wanted to bring it to a more general audience. And the number that matters is not how much RAM you have, but how much RAM you have per CPU cores.
Mm-hmm.
And even at the smallest instances you can get, the smallest Kubernetes pods, you get at least 1 gigabyte of RAM per core. So it could be less than 1 gigabyte of RAM, but if you have less than one core.
Okay, I get your point.
And there is the amount of RAM you have and the amount of CPU you have together is what matters. So, for example, if you use a lot of the CPU, I think to get the intuition is think of a program that uses 100% of the CPU.
Mm-hmm.
How much RAM should it be using and how much does it matter? And the answer is, and again, this is just to give the basic intuition, if you're using 100% of the CPU, truly 100% of the CPU, no other program can run and make use of the RAM at the same time.
Yeah.
So you might as well use 100% of the RAM.
Yeah.
You don't get a prize for using 100% of the CPU and 1% of RAM.
Yes, that makes sense.
So when you capture a large portion of the CPU, you essentially capture a portion of the RAM whether or not you use it. So you might as well use it to save on the more limited resource.
Yeah. I mean, that makes sense, right? Like, if there's a bottleneck and I can use another resource to alleviate that bottleneck, then that will help performance, generally speaking, right? Like, it could also just be that, I don't know, that doesn't make sense, but if I run out of network sockets and can somehow make that problem less pressing by using more RAM, then I would do that as well, right? Like if there's a bottleneck and I can invest another resource to make it less so, then even if the trade is bad, like speaking like, oh, I use all my RAM and all I get is 5% more performance. Yeah, but you wouldn't have gotten those 5% otherwise. What else are you going to do with that resource? Like
Exactly. So the idea behind moving collectors, and again, it's very intentional, is to make a more efficient use of the entire machine. You have to look at the CPU and RAM together.
Yeah.
And the way Java uses CPU and RAM together is very efficient. And so, but there is a problem.
Yeah.
And the problem is that, number one, people need to understand this, and it's very different from other languages. So people think of allocation in Java as if it was allocation in another language, and it just doesn't work the same way. But the problem is that in Java, you still need to set the heap size. You need to tell it how much RAM you want it to use. And in fact, whatever you tell it...
GGC is really strongly working towards not making that.
Exactly. Yeah. So this is a problem that we will be solving very soon. You won't need to do that anymore. And the garbage collectors will figure out on their own what the best amount of heap... You'll be able to tell them, I want to use more RAM or more CPU. But then they'll figure out how much heap to use, and ZGC will probably be the first collector to make use of that, followed by others, probably G1 and then maybe the other collectors.
But then let's talk a little bit about in more detail about how that comes to be. Like, first of all, like I can see immediately how when you say the garbage collector is better than something like malloc and free, because, well, I mean, there are always special situations where just the structure of the data that I have might allow me to do something very clever that is not generally applicable. But if I have general code and I have generally applicable stuff that I need to allocate and then free up, I'm essentially implementing my own garbage collector. Like that's essentially what I'm doing.
Yes,
right?
but it's not. But it's more than that, because with malloc and free, there are algorithms involved. You need to implement malloc and free.
Yeah.
And the implementations of malloc and free these days can be huge, right?
Mm-hmm.
I mean, tens of thousands of lines long.
Okay.
They're not simple mechanisms. And they're working in a specific way, and the way Java manages memory is in a completely different way.
I wanted to get there. I want to say, like, the one reason why garbage collection is probably better is because I will, and if I think I do it on my own, I will probably end up re-implementing something like some machinery that will use and free up memory in my system. And having talked to somebody like Stefan Johansson, for example, on the stream, clearly there's a lot of thought going into that I cannot easily replicate. But you're saying it's not just that. It's not just that somebody invested more time and did it better than I could do it. You also say like there's the moving garbage collector has a fundamental advantage how we can use more memory to save on CPU. And can you give us an intuition for why that is the case?
Yes, and then I'll say how certain low-level languages do allow you to get something similar.
Okay.
So with malloc and free, you have those two operations that in Java's memory management you simply don't have. Mm-hmm. The way malloc works is that it looks for a block of a certain size from some pool and gives it to you, and then free returns it to the pool. The way Java does it, there is no malloc and there is no free. So we just can't think about it in those ways. The way you allocate memory on the heap in Java is you just bump a pointer. It's very similar to stack allocation.
Yeah.
And the way you free in Java is that you don't. It's just the garbage collector simply doesn't know about dead objects. It will, at a certain point, it does compaction and moves. This is why I called a moving collector. It moves the live objects, and because it doesn't see the dead ones, it will just write over them.
Yeah.
But memory is never freed. An object is never freed the same way. It's just a completely different algorithm.
Yeah.
The way you can get that in low-level language.
Before we get there, so you're saying. So Java doesn't do malloc and free the same way. You described like both.
It doesn't have those operations.
Yeah, exactly. But you described like the thing I want to do with malloc, which is get memory for something that's cheap. It's a pointer bump, and freeing up memory is just like that's a real operation because during a compaction, for example, I just overwrite. It will just take the live objects, put it where nothing else alive is, which is probably then a dead object, at least if I ran long enough. But of course, it has to do with the work to figure out what are live objects and all of that, right? So that work is also costs CPU.
Yes.
Whereas and the malloc and free also cost CPU to figure out where those operations. And are you saying that the overall CPU time I spend in a moving garbage collector is just less.
Yes, absolutely. That is the idea behind moving collectors. But to be more precise, it's not that it is fundamentally less, but that you have a knob to turn and you can decide how much CPU you want to spend in memory management, and that is the size of the heap.
But how is that helping me? Like, how is it helping me? I still don't quite get it. How is it helping me if I double my heap size? How is that reducing the CPU load? Because in the end, if I run this program for like 24 hours and I run through the heap space like a gazillion times, wouldn't I have done the same kind of operations in the end?
So if you think about, let's say you have a C program that calls malloc and free and unchanged, and you take a Java program unchanged, and imagine you running them on a machine with infinite memory. The C program will still do malloc and free.
Yeah.
The Java program, so the moving garbage collector, only starts collecting when the memory is exhausted.
Yeah.
So it will never do any memory management. Now, let's say memory isn't infinite.
Yeah.
That work you do to preserve the live objects, you only do work for the live objects. But the number of live objects in your program is more or less constant. It doesn't matter how much garbage you have. So the more, so you need to preserve the live objects, and it's the same number every time, once memory is exhausted. So if you double the memory, you need to do that operation of preserving live objects half of the time. You make it, you increase the memory size by 10, you multiply it by 10. You have to do the same operation 10 times fewer.
Yeah.
So you double the heap size, you do half the CPU work.
That's also the reason then, I guess, because it's funny that the flip side of that I actually do know, which is when you're operating in like 90, 95, 99% of heap capacity for a long time, it'll just thrash your CPU because these are constant collections.
Yes.
And that's basically the situation where I have to do that unit of work, but like a lot. And that then just requires a lot of compute. That intuition I did have, but of course that plays the other way around. Okay, that's interesting. So you're saying I have a more or less constant amount of work that I can decide how often, not constant meaning one collection. One collection is roughly the same time, no matter how large the heap is. And I can decide how often I want to do that by turning the memory knob.
Yes.
That is a good intuition. Thank you. That makes sense.
Now you can get, if you want to get similar efficiency in a low-level language where you have malloc and free, the way to do that is with something called arenas. And it is sort of the same principle where you just let garbage accumulate. So having a lot of garbage in RAM is actually more efficient. So the way arenas work is that instead of mallocing and freeing objects one at a time, you malloc one huge buffer, and then you allocate objects by bumping a pointer inside that arena. And then when some operation ends, you free all of them. The problem is that in most low-level languages, it's not easy. It's not easy to do in C. It's not easy to do in C++. It's not easy to do in Rust. There is one language where that makes it much nicer, although it's not trivial, and that's Zig.
Okay.
So in Zig, you can have the same memory management advantages as you do in Java, but it's not by just using malloc and free. You have to change the way you manage memory.
Okay, sidetrack. Is that arena conceptually the same kind of arena that FFM uses because it uses the term arena for creating off-heap memory? Is there a connection?
No, yes and no. They just use the term arena to mean one large block of objects. So in that respect, yes. But when we say arenas in Zig, we mean how we allocate and free objects, and that in FFM you can do it that way, or you can do it a different way. But you could do it that way.
Okay. What you just basically described is a comparison, right, across different ecosystems. If what you say is so obviously true, I could just test it and see it, right? I could just benchmark that and observe that. Is that...
Yes, yeah, and you will see it, but that depends on the quality of the benchmark, and that is a huge, huge problem in performance in general. I think benchmarks in the last 20 years have become less and less relevant, and in the field of software performance, we say that benchmarks lie, and I don't think people understand by how much they lie. We're talking about lying by orders of magnitude. And that's not because the numbers you get for the benchmark itself are wrong. The numbers for the benchmarks are absolutely true. The mistake is in extrapolating from them. Mm-hmm. So you have a benchmark, you get a result, and you say, oh, so X is faster than Y, then if I do X in my program, it will be faster than Y. And that is just not true. There is an example, someone said, when they heard about moving collectors, they said they tried to do something similar in C++ or Rust maybe, and they showed that they could reach the same performance as a Java program that allocates a lot, but with malloc and free, with no more CPU and less RAM. Uh-huh. And I said, you're wrong. But then I looked at the benchmark, and what that benchmark did was it was allocating objects that are all of the same size, and it was allocating them and freeing them, and allocating them and freeing them. Yeah. And if you do exactly that, then malloc can be very efficient because it will reuse the same memory over and over. Mm-hmm. And then you say, okay, so malloc is actually quite efficient. But that is not true if your program is doing other things and allocating objects of different sizes, and they have different lifetimes, and you just can't extrapolate. And the problem is getting more and more difficult where we have more complexity at every layer. So allocators that implement malloc and free, I guess, are far more complex these days. So for very simple things, they behave a certain way, but after running your program for an hour and your heap is fragmented, they will behave in a completely different way. So what happens in the program, other than what you're doing in the benchmark, matters the same way for garbage collectors in Java. CPU.
Sorry, when you describe malloc and free, maybe you can get back to it, because I was already wondering the way you described it, because I don't know it actually, because Java is basically the only language I know. I was thinking about fragmentation. So is there a step where at some point the system has to say, like, this is not, because you could run out of memory because you want to have a large chunk of memory that isn't available.
I've been programming, so I work on hotspots sometimes, and I've been programming in C++ for many, many years, and memory management in C++ is a huge problem.
So does that mean that at some point I have to start compacting? Because do you remember defragmentation from the Windows days, like in the 90s?
So first of all, changing your allocator implementation, where you think, in Java you have all these garbage collectors, but right, in C or C++ you don't have that choice, but you do, and you see a lot of C++ programs get significantly better or worse depending on the implementation of malloc and free they use. And you can switch it just as you switch a garbage collector in C, because these days those allocators have to be very, very complicated.
Yeah, I mean, just like garbage collectors, right? Like, so
yes, fair, and they can get, programs can get worse over time, and then you have to think or change your allocator. Sometimes it's a problem. Sometimes, if you're an experienced C++ programmer, you might know how to avoid it. But yes, all languages have similar kinds of problems. Yeah. But this level of complexity is not just there; it's everywhere these days. So the compiler. Mm-hmm. You want to see if subroutine A is faster than subroutine B, and you have a micro benchmark for A and for B, and you see, A is 10 times faster. But optimizing compilers these days, if they compile just one subroutine, and if they compile one subroutine in the context of many others, can compile it in a very different way. Yeah. So what else is in your program beside that particular subroutine can matter a lot. The CPU. Also, it wasn't like that when I started programming, in the late 80s. But back then, we could say, machine operation dividing numbers is much more expensive than adding numbers. And that is still true to an extent, but now things are much more stochastic and depend on what else is happening. So, for example, one of the most expensive operations you could do is read from RAM. Mm-hmm. But there could be 100x difference between whether you've recently read from the same address and that is still in the cache, in the L1 cache, or not. And that depends on what other threads are running in your program. Yeah. And another thing, branch predictors. So in the past, you could say, an if would be expensive. These days, it could be expensive. Maybe it's expensive if the branch predictor works. Maybe it isn't. So you just can't extrapolate from the benchmark to your program. And these days, I'd say micro benchmarks and benchmarks in general are completely irrelevant. You can see a benchmark somewhere, and you don't know the relationship between that program and yours.
I think he's talking about a specific kind of benchmark, though, right? When I need to figure out how my application is doing, and I run like benchmarks, like I launch the entire application, run like a test benchmark suite against them. There's still problems there, like finding good data that does not like lean in one direction or the other. But then I do that, and assuming I keep the hardware platform underneath stable, I can see how the performance of this specific thing evolves.
Yes.
But it's more like the comparative benchmarks that you mean, like A is faster than B.
Right. So I'll get to that, and you're absolutely right. That is how you should do things. But when I talk about benchmarks, I mean benchmarks of programs that are not yours.
Yeah.
And those are actually only useful if you are. So I say benchmarks are only useful if you're measuring something that you yourself wrote, and you know how things work, and then you know how to extrapolate them, and you'd be able to say, but if I run under different situations, if I have another thread, if I have more RAM, less RAM, if I've been running this for an hour, maybe the performance, you understand how it works. So how can you improve the performance of your program? You have to measure your program and profile it. And I call that profiling, not benchmarking. You do have some artificial workload maybe, but you'll measure all the operations in your program in the context of your particular program.
Yeah.
And I say that every program these days is a snowflake. It's very hard to extrapolate.
That's not what the Java developer who implements the 100th CRUD application in their life is feeling like.
Right. So it is true that once you gain experience, you can say program A is similar enough to program B that I know I can learn something from program A about program B. But for that, you need to know what affects everything.
But also, I think, would you still say that micro benchmarks can play a role in finding something? So let's say, for example, I profile my application and I find out, okay, so that's usually why you do that. You figure out this path takes too long. Like the latency on this request is too long. I dig into it and I find like there's this chunk of code that just takes up an inordinate amount of time. Can I optimize that? And then you drill down deeper and you're like, okay, so here's like a method that may take a lot of time. Would you say then it's fair to use micro benchmarking as a way to find a better implementation of that method to then plug back into the original profiling? Because like a large program profiling will be all over the place, will be harder to track down individual impacts than if I could, micro benchmark my way into like a good implementation for that method and then hope, or rather measure then, that it plays out in the larger thing.
Yes, maybe. But you've already started out by doing the right thing, and that is a mistake that many people do. You profiled first, and you saw what the hot path of your program is.
Yeah.
The last thing you want to do, let's say Operation X, even in your program, actually takes 10 times longer than Operation Y. Is it worth it to you to replace X with Y?
Yeah, absolutely.
The answer is, we don't know, because if you're spending only 1% of your program doing X, running that operation 10,000 times faster will at best improve your program by less than 1%.
Yeah, and that's all strikes again.
Right. So and if you just wasted time and you made your code more complicated. So the first thing you should do is exactly what you described. First, see where your program spends its time by profiling. We have JMS, JFR, and good profilers in Java.
Yeah.
So you found the hot path, and then you can say, okay, this operation is taking me a long time. Then you can micro benchmark that against something else. Absolutely. But then you're not done. You have to make sure, go back to your program and try the new thing and then see if it actually helps.
Yeah, I never talked to Alexei Shipilev about this, but I don't want to put words in his mouth. But my gut feeling from how he talks about performance is, because he developed GMH, that I would think he might think that this is like a very double-edged sword, because on the one hand, GMH is really trying to make micro benchmarking as reliable as that is even possible, right? He put in a lot of work to make sure that the code that I want to benchmark does not, by the fact of the matter that it is an isolated method, just falls into a trap that, like, for example, I just write a loop that never does anything, and then the just time compiler figures out it's dead code, eliminates the loop, and my performance goes through the roof, and my benchmark is entirely useless. So it gives a lot of mechanics to make sure that stuff like that doesn't happen, which gives me, as the performance layman, the impression that, oh, I'm doing the right thing. And then I might not do the other thing. Because he always says it's the start of a journey. When you get numbers, that's the beginning. Now you have to understand why the numbers are what they are. what that means and what you can derive from that for the larger application. But JMH, looking so snappy and professional, makes it easy to start and end. Start with the JMH, with the, I think, at benchmark annotation it is, and end with the Excel sheet, which gives me the numbers, and be done with it.
Yeah, no, and
I've absolutely done that, by the way, with like stream operations and stuff.
Yeah, JMH is wonderful and it's very helpful, but I would say micro benchmarks are very helpful when you're benchmarking the code that you yourself wrote, because then you know sometimes you might be exercising a particular fast path, like in that malloc and free, that if you do precisely this, malloc is very fast, but if something else happens, then it's not. So if you know exactly how a mechanism works, you also understand whether what it was that you've exercised. Was it just the fast path? Was it a combination of the fast path and the slow path? And then you can put it to really good use. But if your micro benchmark something like streams that somebody else wrote, you can never be sure. And then it's very hard to extrapolate from that and know whether what you got is actually true. And just putting in a blog post is not helpful. I would say even harmful.
That's exactly what I did, though.
a lot of our state. But
I'm sure I caveated it somewhere.
But it is good in the scenario you described before to say, this is actually in my program, and I learned something that may or may not be true in my program. It was true in the micro benchmark, but then you bring it back to your program and you see, did it help or did it not? But I would say micro benchmarks are not generally helpful to measure code that other people wrote.
Yeah. I mean, I also think that many applications in Java, if they are slow for other reasons. They are usually not slow because I'm using the wrong stream operations, or I use a stream instead of a loop, or I don't know. That's not usually the reason why Java applications are slow. I think that there's such a thing as premature optimization. I would say what you should probably keep in mind is something like roughly like Landau symbols, right? Like if you're doing like an n squared thing where you don't need to, then you might start causing problems down the line that are not micro benchmark solvable. You know, just don't compare every user with every card every time you're trying to find which user has which card.
Right, but even then it depends on whether that operation is on the hot path or not. Because sometimes an n squared algorithm is very simple to code.
Yeah.
And if it's not something you do all the time, it's not in your hot path.
Yeah.
It's okay.
Yeah.
So the most important thing is always to profile first. The difference between a fast program and a slow program in any language is whether that program has been profiled or not. Because otherwise, if you profile, you know what it is that you need to optimize. Yeah. And if you don't, either you optimize nothing or optimize the wrong things, and just code becomes worse, and it's just not helpful. So always profile.
Yeah, and I think other reasons why Java application might fall into traps is something like maybe they're overly synchronizing on something. Maybe they have a data structure that should be synchronizing on that much. I think it's not usually things that are solvable by a micro benchmark in the first place, because most Java programs are not that compute intense. It doesn't matter how much time I spend on the loop over my 100 users that I just load from the database if I loaded them from the database.
And Java is very, very fast.
I mean, I'm not even trying to compare Java to another language. I'm just saying like a Java program not being slow compared to a C++ program. I'm just meaning somebody having the feeling like my web backend is maybe a bit slow. I would say very unlikely that it's because you picked the wrong stream operation. Much more likely that, pick the wrong kind of algorithm, or maybe just pick the wrong data structure.
But there's no need to guess.
Measure, exactly.
Profile and measure. That would say, don't guess.
Yes.
Measure with a profiler, and then you'll know.
Yeah. Is that a good endpoint, or something more you want to add to that?
I don't know. Up to you.
What? I'm the noob here. You're the one bringing the interesting tidbits. So
no, I think.
Okay, so we're done. Good. Thank you very much for being here, Ron.
Thank you, Nicolai.
Well, you know what? Let's chat a bit. What are you working on these days?
Things I don't think we can make public
yet. So there's nothing to share. Nothing like not entirely offhand with structured currencies. Alan Bateman took that all over.
Yes, it's mostly Alan. We actually, with structured currency, we wanted to make it permanent in the next JDK. Unfortunately,
you have to put a number on that because we're not sure when this goes out. So we, at the time of recording, 26 was recorded 2 days
just come
ago.
out. So we wanted to make it permanent in 27. I think it's not going to happen because we want to make a small change. But some people want to be better safe than sorry, and they want to preview it again. So we'll see.
Okay. All right, like you guys at your behind the scenes stuff. Okay, good. I'm probably going to cut this from the conversation. Okay. Thank you, Ron.
Thank you, Nicolai.